Welcome friends, in this one we're going to talk about this matrix and these vectors, and we're going to discover what an eigenvector is. So let's see. You have this matrix and let's take a look at this vector u. What is the relationship between these two? Well, to check that you just simply have to see what happens when A acts on u. So we're going to do that through multiplication. I'll type here 1 and then 2 and then 3 and then 2. Next to it I'm going to put my vector there u. So 2 comma 3. Now let's carry out the multiplication of the vector by the matrix to see what the results are. So it's going to be a 2 by 1. And the way to do that, remember, is as follows. You're going to take 1 and you're going to multiply by 2. So that's going to become 1 times 2 in this position. And you're going to add to it this 2 times that 3. So it's going to be plus 2 times 3. On the bottom, you're going to do 3 times 2. And then you're going to do 2 times 3 in that position. So it's going to be plus 2 times 3. Work this value out. So again, it's going to be a 2 by 1. Now 1 times 2 is 2. 2 times 3 is 6. You add them up and you get a value of 8. 3 times 2 is 6. 2 times 3 is 6. You add those up and you get a value of 12. Now take a look at something here. I'm going to write this vector next as follows, because we need to be able to see our relationship. 8 is the same as 4 times 2. 12 is the same as 4 times 3. Why do I want to write it this way? Look back at our input vector. It had an entry of 2 and an entry of 3. Now, A12 is actually, as you can see, 4 times 2 and 4 times 3. In other words, I could write this because there's a constant value of 4 being applied to both elements. In other words, I could write this as 4 times 2 by 1. That would be 2 comma 3. And this 2 by 3 right here, let me kind of emphasize it in red. Notice it's the same as this input vector of 2, 3 right there. That's telling you that this output vector A12 is a scalar multiple of the input vector. The specific scalar is 4 right here. Now, let's look at this in a graphical setting so we understand a bit more geometrically what this is telling us. Begin with the input vector of 2, 3. So mark it up here. Now I'm going to have to zoom out because I got to make sure I can fit enough for later use also. So grab an arrow. Remember, vector in the plane is represented often as just an arrow. And then mark up that vector 2 comma 3, so it's about 2 to the right and then 3 up, which is roughly in the middle right here. That's 2, 3 this way. This new vector A12 is 4 times that vector. So I'm going to indicate that by making it blue. Take a look. So the new vector is 8 to the right and then 12 up. 8 to the right and then you go 12 up to here. And what's special then about the red vector, aside from the fact that it's not perfectly aligned here, because I had to estimate the value of 3, is the following. That the blue vector is just a scalar multiple of the red vector. So that red vector is, for that reason, called an eigenvector. In other words, when the matrix acts on it, all it does is that it stretches it without changing the direction of it. Let me fix up the alignment of A. I had to eyeball or estimate the value of 3, that's why it doesn't seem like it's perfectly aligned. Let me just remove this one, because now we know what the bigger one is. That's just an effect of estimating things. So really it should be, perfectly aligned with this one. See, like this. Let's say it goes in this position. There you go. So the blue one is just a multiple of the red one. Same direction. Let's zoom back out here. Now let's look at another example. Let's see. So what I'm going to do is I'm going to take this matrix. I'm going to make it act on this vector v, -1, +1. And let's see what we get out of that operation. So now let's multiply them. So it's going to be a 2 by 1. And go through the process. So it's going to be 1 times -1, which is -1. And then 2 times 1, which is 2. And then it's going to be here 3 times -1, which is -3. And it's going to be 2 times 1, which is 2 in this position. So then it's going to be a 2 by 1. So -1 plus 2 is +1. -3 plus 2 is -1. And take a look. So the original, remember, is -1 comma 1. Let's indicate this in the graph. Let's see. I'm going to use green for that, for the original. So I'm going to have to estimate it because I don't have a -1 here, +1. Everything is by 2's. So we estimate it to the best of our ability. I'm going to go 1 to the left, which is about here, and then 1 up, which is about here this way. And now the new vector is 1 comma -1. So I'm going to show that, say, in, let's see, in black. So it's going to be 1 to the right, 1 to the right, and then 1 down this way. You see? So in other words, this vector right here, this input vector, I'm going to emphasize it in red, is related to this vector right here, the output vector, by being a multiple of it. In other words, take a look. 1 comma negative 1 can be written as negative 1 times the 2 by 1 vector negative 1 comma positive 1, which is the original input vector. So the scalar multiple here happens to be negative 1. So the 1 basically ensures that the size remains the same, but the fact that there's a negative flips it. So you see the black vector now points in the opposite direction of the green vector. So in other words, what we would say thus far is the following, to summarize all of this work. Right, the vector u, like this, and vector v are both eigenvectors of the matrix A. Alright, for the reasons that you see, the reasons are simple. When the matrix acts on these vectors, it simply stretches them, or stretches them and then makes the direction opposite 180 degrees to the original. But that's about it. Now, does it mean that it's like this every single time? Take this vector 0, 1 as an example, and make the matrix act on it to see what the output would be. So let me make a copy of the matrix right here, and put the vector next to it, so that's 0, 1 right here, and multiply this out. It's going to be a 2 by 1. So when you carry this out, it's going to be 1 times 0, which is 0, plus 2 times 1, which is 2. That's going to be 3 times 0, which is 0, and then 2 times 1, which is 2. That's 2. Take a look at the picture that goes with this. It's a little bit different, so I'm going to use a grayish color for that. 0, comma 1, that's like saying an x of 0 and a y of 1. So roughly speaking, it's this vector, this gray vector right there. And the new vector is 2, comma 2. That vector basically lies like this. It's going to be 2 to the right and then 2 up this way. You can tell that that vector is not a scalar multiple of the input. One is pointing in the vertical direction and the other one is now pointing off to the side. So in other words, it's not like the matrix took 0, comma 1 and produced a vector by stretching it that points in the same direction as the original. It's not pointing in a different direction. So what we would say as a result is the following, that W here is not an eigenvector. So in other words, what we would say is the following, that W is not an eigenvector of A. So a simple way to think about eigenvectors at this level of explanation, as you can see, is when a matrix acts on that vector, it simply stretches it, or potentially stretches and flips the direction 180 degrees. Lastly, let's summarize this in a mathematical format, so that would look like the following. An eigenvector of an n by n matrix is a non-zero vector x such that the following is true. In other words, A times x, so let me bold this because it's meant to be a vector right there, is equal to the following. Some constant, so that constant is often called lambda, and then times x this way. Let me stretch this out right there. So when ax and x, it produces x, but it's scaled by this factor lambda. So in our examples, lambda for the first one was 4, for the second one was -1, and then for the last example, there is no such lambda because the vector was both stretched essentially, but at the same time rotated away from its original direction. Right? This gray arrow became this gray arrow right there. That's it. So if it's been helpful, friends, please leave a like and subscribe. Thank you so much for watching. I'll see you in another video.